All right, so let's think about using these simulations to see the principles behind the shape of the S-DOM. One of the things we saw is that sort of no matter what the shape of the parent population, what do we find? S-DOM tends to be normal. But wait a second, we really only tested that for n of 16, right? Maybe 16 is somehow like special. Maybe there's, maybe what about for like n's of 2? Is this also going to be normal? Well, let's try that. Oh, look at what we see. When the n is very small, this does not tend to be normal. What about an n of 5? Okay, so that looks a little more normal, but not really that nice normal distribution we saw with 16, right? What about 10? Okay, now that's starting to look a little bit more normal, right? So what we see is that as long as n tends to be reasonably large, and, you know, I don't know if there's a magic number, but as long as n tends to be pretty large, you tend to get a normal sampling distribution of the mean, right? So that's definitely one thing. So there's a couple of conditions. So these conditions have to be fulfilled before this is true. So samples n, the sample size, must be reasonably large. So 2 is too small. 5 even is a little too small. 10, it starts looking better, but, you know, whatever reasonably large is, it should be reasonably large. A lot of times people use the rule like 40 to be, any n of 40 to be like reasonably large, right? But, you know, that's just a rule of thumb. Okay, what else? Does it matter? So we looked at sample size. That might be an important thing. But what else might matter? Does it matter how many times we sample? So let's see. Let's clear the bottom 3. And let's only do it for 5. Right? So if we only did the simulation 5 times, then we wouldn't get a normal distribution, right? Only when we start doing it like 1,000 times, or 10,000 times rather, or 20,000 times, does it start looking more and more normal, right? So it also seems to be that the more simulations we have, sort of the better. So if using simulations must have a large number of simulations. So, this is true only if n is reasonably large, and only if you have a very large number of simulations, if you're using simulations, right? And so, although this is really helpful, there are some conditions that you have to meet before you could invoke this. Great. So we learned some things from using simulations about the shape of the S-DOM. Okay, so what about the principles behind the center or mean of the S-DOM? Okay, well, one of the things we found was generally the mean of the S-DOM, and I'm going to show you a new notation for this. The mean of the S-DOM is shown as mu sub x bar, because it's the mu of a bunch of means, right? The mean of the S-DOM tends to equal the mean of the population. Sometimes I'll say parent population, but that means the same thing as the population. And that is symbolized by the mu, just plain old mu. Now, notice that this is using mu because remember, SDOM and all sampling distributions are theoretical distributions, right? And theoretical distributions tend to be notated just like populations, right? Now, does it have to be that, are there any conditions, right? So I'll put conditions. Does n matter? So first we'll test this. We want to know if it matters the size of our sample. Okay. So let me clear the lower three. Let's do skewed, right? So let's see if it matters whether the size of our sample matters. Let's try for n equals 2. And let's do that 5 times or 10,000 times. All right. So n equals 2, and this does not look very normal, but the mean is still very close to that mean, right? So that's interesting to note. What about for uniform, right? So n is 2. Is the mean very similar to this mean? Yeah, it tends to be very similar. Okay, so for small n's, the means tend to be equal to each other. What about for n's of 5, which is also still pretty small? Let's try 10,000. Okay, 16 and 16. Still pretty good. What about for skewed? Let's try 10,000. Okay, pretty good. All right, we're seeing something. What about for very large n's? Let's see about that, right? Okay, 8.07, 8.08, right? What about for some crazy custom distributions, right? Okay, 15.06, 15.05, pretty good. Okay, so for both small and large n's, the means tend to be similar. Let's try with this crazy distribution n of 2. 15.04, 15.05. So we're seeing something here. We're seeing that sort of no matter the size of the n, the means tend to be equal. So does n matter? No. For both small and smaller and larger n's, mu sub x bar equals mu. That's nice, right? So it's like we don't have to make sure that we have a large n in order to invoke this principle. Okay, what about does number of simulations matter? Well, let's go see. So let's clear the bottom 3. Let's say we only did 5. If we only did 5 simulations, we get 15.61, which is not that far off from 15.05. Let's clear that again and do another 5. Here we get 11.22, and here we get 15.05, right? So here we see that, well, maybe the number of actual simulations does matter. Here we get 15.79, which is not so bad. Let's clear it and do it again. 16.47, 15. Yeah, so we're seeing that, if you only have a small number of simulations, then you're not really sure if it's really, really close or not. It might vary a little. Usually it's sort of in the right range, but having more seems to give you that assurance. Yeah. But let's try with a larger n. With a larger n, we see, okay, 15.05, 15.03. Okay. Let's clear that again. I'm going to do that simulation 5 times. 15.03, 15.05. Clear it again. Hit 5. 16.51. Okay, so that's off. Let's do it one more time. 16. Okay, so we do see that number of simulations matter. Yes. Having a large number of simulations gives, let's say, more accuracy in mu sub x bar. So in the sample mean. So by accuracy, I mean more of a match between the mean of your sampling distribution as well as your population mean. Okay, so n doesn't matter, but the number of simulations does.